Very good morning to all of you. Today we are going to learn a little bit about a linearity measurement in analog circuits, and we'll try to see how those measurements can be done in Cadence Virtuoso. So if this is an amplifier, right? If I give an xt input and if I assume that yt is the output in the time domain, it is known as linear. It will be known as linear if the output is given by alpha 1 to xt, where alpha can be an integer or a fraction. So as long if you see if it meets this criteria, the output will be a faithful reproduction of an of the input, right? If it's a sine, you get a sine out here. So there is no distortion. So as long as alpha 1 is constant and it's an real number, right, there won't be any distortion. It will be just the amplitude may be scaled up or scaled down, but essentially the output will be a faithful reproduction of the input signal, right? This amplifier will be known as non-linear if the output is distorted, and then you have the higher harmonics of the input. This usually happens when the transistor is coming out of saturation, or the gain is changing because of the input signals and things like that. So if you have designed an amplifier that would work in the linear region for an specific input levels, right? If you cross those input levels, then the transistor will get in come out. Some transistors may come out of the saturation region, or there could be diodes in the or non-linear elements like diodes in the circuit and all those things, and then the output gets distorted. It is no more a faithful reproduction of the input signal, and that's where we say non-linearity has set in. So for only for a specified input levels, we can expect that the signal is linear. Now if you see, if I plot, this is the input. I'm increasing the input power here. This is the output power. So if you see, this is for an ideal amplifier where the ratio of the input to output is constant. So the slope is constant. But normally in all practical amplifiers, after certain input level, here if you see here, from here, the gain is reducing out here. The gain is reducing out here. So the measure of linearity is one of the measures of linearity is 1 dB compression point. It is a point at that input level out here. If you see here, if I extend this curve here, the difference here is 1 dB. That means as compared to the ideal linear output, the actual output available is 1 dB lower. So this is known as input referred 1 dB compression point, and this will be known as the output referred 1 dB compression point. So this is an extrapolated line, right? This is an ideal. So this we can't actually implement these in real life circuits. This is what actually happens in a real life circuit, where the gain starts getting rounded off out here, right? So it deviates from the ideal. So this is 1 dB compression point, right? So in Cadence, when we do the measurement and when we plot, we will see this is the actual gain plot, right? This is how it is going to get from here. It is getting rounded off and getting saturated. Right, to get this point, what the plot would show is it will show one more here, right? One which is 1 dB lesser from here. This is so this is the gain plot in the linear region. So the Cadence would plot, when we do the 1 dB compression point, it will plot one more line out here, which is 1 dB lower from here. So the intersection of this point is actually this point, same point, right? So you will get the 1 dB compression point out here. So here, if these two lines are shown, only these two black lines are shown, then we don't get the intersection point, correct? So what it does is, just to facilitate us to view this thing properly, it will draw one more line out here, with the same slope here, but it is 1 dB lesser in the y-axis. So it will plot this. So the intersection point will give us 1 dB compression point. So let's discuss some of the circuits first, and then we'll discuss three variations of the circuits, and then we will plot the 1 dB compression point for all those three circuits. Now to do the 1 dB compression point, and I have removed the source and put a port here, and I have also connected a port at the output. Now if I see the properties of this port, I have taken an input resistance of 50 ohms, I have taken a sine, I have taken one frequency F1 of 1 kilohertz, and I am giving the amplitude as V in, which is a variable, because in the PSS analysis, in the 1 dB, we are going to sweep this input power and see what is the variation. Okay, so I am taking this amplitude, okay, as a variable V in. Okay, so that's the input port, and at the output port, okay, I am taking it as 500K because this is an CS amplifier. This can't drive low loads. I have connected a very large load out here, so that the gain is not a function of this load, and I have taken it as 500K, and the source is DC type. Okay, so that is the. Now I go to launch AD Explorer, and now I'm doing a launch Explorer. Okay, and then create a new cell view. Okay, right. Okay, how do you want to exist? Okay, my previous simulation, I'm just overwriting it. Right here, variables copy from cell view, so that V in has come in here. So we need to give some default value here. So I'm giving it as -10 out here. Analysis. Okay, choose. So I'm going to choose PSS analysis, right? And here I'm giving it as auto calculate. Number of harmonics, I'm giving it as 10, right? And then sweep, right? I am going to sweep. So select the design variable which I want to sweep is V in. So I'm starting it at as minus 50, right? Here I think I can give an conservative also is an option. Yeah. Now let me tick moderate out here. Okay, and stop it at is at 0, and number of steps. Okay, number of steps I'm going to give it as 100. Okay, and then okay, and then I'm going to run this simulation. So this the simulation is running out here. Since it's moderate, maybe it's taking a little bit of time, right? I go to direct form and main. Okay, here I will go for compression point. Okay, now port output power 1 dB compression, input referred at 1 kilohertz, right? Select this thing on the so I'm going to select this port. So I'm going to select this port. So I am getting this 1 dB compression point plot out here, right? So you can see that the 1 dB compression point is at -16. If you see here, this line is a first order line, which is from here 1 dB below this line has been plotted. So the intersection is at -16.5 dBm, right? So this is for the very first circuit which we saw. So what is the value which we are getting is -16.5 dBm, right? So I close this now out here. Now I'm going to change this, right, to 10 micro. So this is going to get my operating point here close to 0. So the linearity will be adversely affected, right? So the linearity should come below -16. Okay, so it is going to spoil my linearity because I have brought this operating point. Initially it was at VDD by 2, and now I have pulled it below. Okay, so this is going to spoil my linearity. So I do an run again out here. Right. So results, direct plot, main form, right? And I'm choosing this port again. Okay. So I am running this Maestro again. Okay, I go to results, direct plot, main form. So again I am doing a compression 1 kilohertz. Okay, select the plot. This is so now if you see here, this is first order, it has gone to minus 22 dB. Earlier I had minus 16, now it has deteriorated and it has gone to minus 22.9 dBm, right? So earlier we had biased it exactly in the if you see here, earlier we had biased this DC operating point close to VDD by 2. So we got an 1 dB compression point of minus 16, and now I am biasing this, okay, by increasing the width of this transistor from 3 micro to 10 micro. So we saw in the transient analysis also the non-linearity set in earlier itself, right? That can be seen here in the 1 dB compression point also. This non-linearity, right, the 1 dB compression has been lowered to minus 22.9 dB. Now let's take the third circuit. Let's take the third circuit. Now here we had introduced an resistor out here, source regeneration resistance, and we brought down the gain while the operating point was kept at somewhere VDD by 2, but the gain is reduced to almost 2. So and hence we saw in the transient analysis it gave a better linearity. Even for around 200 millivolt signal, the output was not distorted, right? So obviously when we do 1 dB analysis, it is expected that it would be better than, I think we got minus 16 there, so it should be better than minus 16. So let me run this simulation again out here. The same PSS what we did earlier. We are going to do that now. Okay, results, direct plot, main form, right, and we are going to do compression point, right, and at 1 kilohertz, right, and we're going to select the port out here. Now if you see here, it is gone, it is improved now, right? From minus 16, the 1 dB compression point has come to minus 9.1, right? So in the first circuit we got around minus 16, and when we brought down the operating point close to 0, it went probably to minus 22 or something, right? And now in the third circuit we reduced the gain, so from minus 16 we have improved the 1 dB compression point to around minus 9. Okay, there is another figure of merit to define the linearity, to measure the linearity, which is known as third order intercept point. Now if this is an amplifier, right, with gain and there is no distortion and it is completely linear, and I give two frequencies F1 and F2, they will get I will get F1 and F2 out here, right? But in case there is any linearity, so this is going to be the output equations. So you see x square, x cube, and those things are available, right? So that will cause all these unwanted frequencies coming. So the closest frequency from the desired frequency will be 2f1 minus f2 and 2f2 minus f1. Okay, these are the two frequencies which if these two frequencies are very far away, then these also will be far away and you can filter them out. Okay, so that's not a problem. But if these two desired frequencies are very close to each other, then these unwanted harmonics also will be close to each other. Okay, so this needs to be if we measure the relative strength of this and these signals, okay, relative strength of these signals and these signals, then it will give me a measure of the linearity of the circuit. Okay, if this is much stronger than this, that means this system is more linear. Okay, so how do I do that? See these two signals, and they are going to the growth rate is going to be 3 dB for 1 dB increase in input power level, whereas this grows, right, 1 dB per input level. Okay, these signals. So if you plot, extrapolate these graphs, okay, 1 dB and the third harmonic plot, right, the gain of this and the gain of this, okay, these two. If I plot the gain of this and gain of this, and if I extrapolate this, they will meet here, okay, at this particular point, okay, the signal strength of this and this frequency will be the same, right? I can't give an input signal more than that, okay. So that is after that it is going to deteriorate my signal, because this signal, this unwanted signal, will have more strength than the wanted signal. So this is an figure of merit which we plot, right? This is the extrapolate. This will also get rounded off actually, but from the linear region here, okay, if we extrapolate, and they will intercept at a point which is known as the third order intercept point. At this point, okay, the gain of these desired frequencies and the gain of these undesired frequencies will be same. So we will try to do a simulation in Cadence and see. So these two frequencies, I am going to set as 10 kilohertz, and the second frequency, okay, this is F1 actually, okay, let me change that as F1. This is the first frequency F1, and the second frequency is 10.1 kilohertz, okay. Now the third harmonic, okay, this particular frequency is 2F1 minus F2, that is 2 into 10, 20 kilohertz minus F1, F2 is 10, which I get 9.1, okay. So I am going to plot the power of this, okay, it is symmetrical. So one I am going to check the power of this particular signal, and and that is known as third harmonic, and the first harmonic, I am going to take this signal, okay. I am going to measure the relative power of this with respect to this, okay. I am going to compare this power. So the second one I am going to take as 10.1 kilohertz, okay. So because I have given 10 kilohertz and 10.1 kilohertz, okay, 9.1 is this unwanted signal, and this is 10.1, again one of my desired signals. This is the primary signal, I am calling it like this. So I am going to do a plot, and then from the cadence I will see these two gain plots are going to get intercepted here, which will be known as a third order intercept point, which is again a figure of merit of linearity. So we are going to analyze the same circuit which we used for the 1 dB compression. Now for the third intercept, what we are going to see, we are going to change this properties, okay. Now if you see here, there is an option for display second sinusoidal, okay. Earlier we didn't do that. Now I am going to do display second. So first frequency I am setting at 10 kilohertz, the second one F2 as 10.1 kilohertz, okay. Amplitude in dBm, both I am giving as V in, okay. So that's done. Then I go to launch Explorer, okay, create new, okay, yes, right. So variables, copy from cell view. So I got this V in out here. So I'm giving a default of -10, okay. Analysis, choose, and now this time I am going to choose QPSS, okay. Now I see both these frequencies listed out here, so I have to select one as large, okay. I can't have both this, so I'm assuming this to be my main frequency. I am setting it as large, both cannot be moderate, so one I need to set it as large, so I have done that, all right. And then sweep, right, I need to define the sweep. So design variable, so I am going to sweep a V in out here, okay, and I'm going to start it as at say -30, and then I'm going to stop it as at 20, and a number of steps, okay, a number of steps I'm going to, let me just make right, let me take it as -40 or yeah, let it remain -30, no problem. Number of steps I'm going to put it as 100, okay, and then I'm going to run this, right, update and run. So this is going to run the simulations out here. Right. So I go to results, direct plot, and main form, right, and here now QSS, like we did this QPSS simulation, and I am going to do IPN curves this time. Okay, so port is fixed, and here it is single point, so I have to change that to variable sweep, right? V in has been swept, and it shows, okay, it is from -30 to 20. Now I got to set the third order distortion, like we said, it is to be set to 9.9K, and this is to be first is going to be set as 10.1K. That's what we did, right? And then select the port. Okay, now I am going to select the port. Right, so I'm getting this, right? So if you see here, these two curves, white curves, they are intersecting out here. Okay, so you see input referred IP3, okay. I am not sure why this is tagged out here. If you see, this value is not changing. Okay, it is fixed 1.08, and where did this get 1.08? If you see, both of them are intersecting out here. This is 0, and this intersection point is nothing but 1.08. Okay, so this is the input referred IP3. Okay, where both of these curves are getting. So this is another measure of linearity. In the next class, we would talk about total harmonic distortion. Okay, so that's all for today. Thanks a lot.